application here. Okay, you got it? Okay, test 1, 2, 3. So yeah, we're recording this for posterity among others. But I'd like to introduce to you Professor Dragan Maksimovic from the University of Colorado Boulder, who we've invited today to give a talk in accordance with our Granger Lecture Series. Professor Maksimovic got his doctorate degree at Caltech longer ago than I'll impose on him. And since then, almost the whole time has been at University of Colorado Boulder. At present, he is the Charles Schelke Endowed Professor, and he's also director of the Colorado Power Electronics Center. He's done a lot of work in circuit level kinds of things, in integrated circuit level kinds of things in power electronics, and is well known for a lot of the work that he's done in control, modeling, simulation, and actual device work. And there's a significant team at Colorado, has been for quite a while, under Bob Erickson and Dragan Maksimovic, renowned for power electronics really from a kind of a circuits perspective. So with that, I'll turn it over to you. Welcome.
Great. Thank you, Phil. Thank you all for coming today. It's really a pleasure to come and visit the school. I haven't been here for all these years that I spent in Boulder in the U.S. I've been to many different places, but never to University of Illinois here. So again, thanks to Phil for arranging this visit. So as Phil said, my background is power electronics, and really from more of a circuit point of view. But we do obviously do projects that have a relationship of power electronics to the power systems. And you will see some of the applications that we have been interested in. So I asked at the very beginning if you guys are all from power electronics area, and I actually know some of you from various conferences. But I understand some of you are just from circuit design perspective and maybe some devices and so on. So I'll try to make this be power electronics centric, but with a slant that's towards, anyone can really see what I'm talking about. Let's see how that works. So just to lower your expectations a little bit at the very beginning, we're going to start off with something that's super simple. And along the way, I'm going to ask you some questions. So listen carefully, and then I'll wait for you to answer. So what do we say is power electronics? It's basically a combination of semiconductor devices operating at switches and magnetic and capacitive energy storage components arranged in various ways so we can perform electrical power conversion in whatever form we like. And this particular form is taking a DC input voltage and doing the magic switching between these two devices and creating an output voltage that happens to be greater than the input voltage. Again, for those who are really in the power electronics area, this is something you would see in a very introductory class. So switching occurs at some switching frequencies, switching frequency right here, and the way the converter is controlled is through a duty cycle. One thing that I'd like to mention immediately is what we call a DC conversion ratio. From input voltage to output voltage, the ratio is what we refer to as M. Historically, I have no idea where this M comes from, but that's what we've been using as a DC conversion ratio. And for the boost converter, it happens to be dependent on the duty cycle of this bottom switch in the form of 1 over 1 minus D. Okay, you can do very basic circuit analysis and prove to yourself that this is indeed the case. All right, so for an undergraduate circuit student, it is actually somewhat unusual to see some entity that is capable of generating a voltage higher than the available supply voltage. That's what when I teach undergraduate classes, there's a little bit of a surprise there because they think it's just impossible to get voltages higher than the supply that's coming in. It is, and the boost converter is a way to do that. Okay, so now in power electronics, what do we care about? There's really one thing we care about the most, and that's efficiency, right? So these entities, the power converters taking electric power from one form and converting to another, are supposed to do that really, really efficiently. Otherwise, the purpose of shaping that power flow through is lost because the efficiency of the converter is really what determines how useful that entity is in shaping the output. Now, I'm showing here a design that someone has done. Let's say one of my students, very skilled person in power electronics, has done a design of a boost converter and has measured or modeled efficiency of the converter and shown that efficiency in two different forms. Here is efficiency, and you see numbers between 80% and 100% as a function of fractional power, right? From 0%, from 10% to 100%. And you get these curves, and these are typical shapes of curves we get for efficiency. The curves are shown, however, for three different conversion ratios. So if you don't want to boost at all, you get this top blue line. If you want to boost by a factor of 3, you get this red line right here. If you want to boost by a factor of 10, you go down to this line right here. Okay? Now let's reverse that and say we want to have efficiency for that exact same converter for a given power level as a function of conversion ratio. Okay? So we have here efficiency as a function of conversion ratio for three different power levels: 10% power, 100% power, 50% of power. All right. So you look at these and say, well, this is maybe not that bad, right? So our efficiency is, it can be greater than 90% for the most part. Looks like we are doing reasonably well. Again, this is the type of design we can do using state-of-the-art techniques that have been practiced in power electronics for decades now. The question I want to ask you right now is the following. When we look at these curves, there is a trend that's unmistakable. No matter how skilled designer you are, you're always going to have the exact same qualitative behavior. That efficiency goes down the more you want to step up. So higher step up results in lower efficiency. And second, operating at the lower power level also results in lower efficiency. Look at these graphs right here. For a step up of 10, at the low end of the power, we get efficiencies only in the 80s. Okay? If you go step up by a factor of 3, you get better results. If you don't step up at all, you get actually really superb results. So fundamentally, why is the boost efficiency lower for higher step-up ratio and for lower power levels? What do you say? And this is mainly a question for those who have done some power electronics. What do you think? It's a boost converter. You want to step up more, you're going to have lower efficiency. Fundamentally, why is that the case?
Power electronics students are supposed to know which page this is on in the textbook.
All right. You don't need to recall. Just think aloud. Whatever you say, I'm going to tell you that it's wrong. But just go ahead. All right. How about you? Just do circuit analysis, right, and find out what the losses are. Where are the losses coming from, by the way? What losses do we have? Yeah. All right. Great. Right. That's the power electronics answer to that. So we have switching losses because these devices are commutating between on and off state. We also have conduction losses of current going through, some resistive components associated with the magnetics, on resistances of the MOSFETs. And so we are going to have losses of conduction and switching type. So if you do detailed circuit analysis of losses, you find out that indeed, relatively speaking, the losses are in fact increasing compared to the power processed more if the step-up ratio is higher. And you really can't beat that. So there's got to be something more fundamental behind this. Why are we not able to maintain the same 99% efficiency regardless of how high the step-up ratio is? Okay. So I'd encourage you to go back and actually do the detailed circuit analysis and model losses in the converter of your choice and convince yourself that this detailed work actually does show that. But what I'm going to show you next is actually going beyond that detailed circuit analysis into more fundamental principles behind power conversion. So it is customary to have a power electronics seminar and bring up some obscure, really old references. This reference from Dan Wolliver is from 1969. It's a PhD thesis at MIT. As Phil mentioned, I'm a Caltech graduate, but I do have the courage of giving some credit to MIT as well. So this is an important thesis because it was done in a very, very early stages of DC-DC conversion, and then ask questions from a more fundamental point of view rather than how best to build a circuit, right? So the questions he asked were how much power needs to be processed by these nonlinear components, the switches, in order to achieve a certain conversion ratio, okay? And surprisingly enough, there is actually a fundamental theorem answer to that question. There is a lower bound to how much power has to be processed by the switches in order to achieve a certain conversion ratio. There are further bounds on the switch stresses that are unbeatable. No matter how clever you are and how you construct the circuit, there are lower limits on the switch stresses that you cannot break if you achieve a certain DC conversion ratio. And finally, there is also a certain amount of reactive power, a certain amount of apparent power processed by reactive components that has to be maintained in order to achieve a certain DC conversion ratio. So these are all really nice results because they teach us what is impossible and they teach us what is the best possible case. All right. Now, the diagram that is shown right here is a direct copy from the thesis, and it shows an input voltage and the load where you created the output. And what is happening in between is a DC-DC converter is in a very generic form. For what happens in all DC-DC conversion are actually two power paths. You can visualize them as being what is called direct power processing from input to the output, and there is indirect or AC power processing that has to go through the nonlinear, in particular, switching devices. All right, so when you look at this indirect power path right here in the theory that Dan came up with, you see that there are actually two components to it. The first component is a nonlinear element or a switch that is taking DC power and converting to AC. A single switch is fundamentally operating as a DC to AC inverter. Now, to get the DC back, you have to have a switch that does the opposite, that does the rectification part, and that is this DC component right here that is taking AC power and then putting that back into the DC form. This indirect power path of converting DC into AC internal to the converter and then back into DC is a fundamental component or function to any meaningful DC-DC conversion. And I should say, I believe you can make a very general statement that everything that we've done in power electronics since is attempts to make the indirect power processing as efficient as possible. So you're going to hear two statements from me. One is to make really efficient power processing, we want to minimize indirect power, and second, process indirect power as efficiently as possible. Okay, so that's the answer to fundamentally why we see that in a boost. The more you step up, it turns out, the more indirect power you're processing and more losses you have associated with that picture. When you look at the diagram again, one side comment is that we have a formal proof that it is impossible to construct a DC-DC converter using a single switch. All right? So once you know that, there is no reason to spend time trying to sketch things. It's just impossible. Don't try, right? Okay, let's see how that applies to the case we are talking about, this boosting, and what is really indirect or AC power. So the way we really find out what is the amount of indirect or AC power processed by a switch is really simple. You can do it on your converter of choice. There is an example for a boost. So you take the boost switch or the switch waveforms, right? So here is the waveform of the switch voltage and the switch current. And you subtract off the DC component of those quantities. So take out the DC or average value of the switch voltage, take out the DC or average value of the switch current. What is left over are AC voltages and currents. When you do the product of these two, these AC quantities, the switch voltage and the switch current, you get the AC power processed by the switch. Look at this switch right here, and you look at the waveforms. Here we have negative AC voltage. Here we have a positive AC current. The product of the two is a negative value. Does that make sense? It makes sense in the following, right? So this device is generating AC power. The AC power that is absorbed by the device is negative, which really means the device itself is fundamentally generating AC power. Which device is going to be consuming that AC power? So we have Q1 here generating AC power. Which device is going to consume AC power? Q2. How does it do that? Well, there is this intermediate energy storage that is shuffling AC power through. So you have an intermediate increase and decrease in energy in the magnetic component, and that's the mechanism by which the converter, in fact, fundamentally achieves a step-up conversion ratio. The more indirect power you process, the higher step-up you're going to be able to achieve. But in the process, you're going to have losses that are higher as well. All right, so we can actually construct what is called a boost average switch model. The average switch model of a boost converter looks like this. It looks like a circuit, right? You have input voltage, you have this inductor in here, and then the function of the switch is DC-wise is represented by an ideal transformer with D prime to D DC conversion ratio. The entire AC power is going through that transformer. That's what happens in the circuit. So this is really just a different way of viewing the converter operation for those of you who have seen that in the introductory power electronics classes. But it is quite revealing because we can make some really general conclusions from this single example. So in the boost case, direct power is just the input voltage times output current. If you short circuit the input to the output, you get a conversion ratio 1. How much of the power is direct power? The entire power is direct, right? So short circuit is the best converter you can imagine. It has highest efficiency. Unfortunately, it doesn't do anything, right? So the highest efficiency is when you have fully just direct power. Because what we have associated with direct power is only DC conduction losses. Now, when you start switching and consuming DC power, producing AC power by the switch, and doing the reverse with the rectifier switch, you're incurring losses in the process. So the conversion from DC to AC is obtained by switching the inverter transistor Q1. There is going to be energy fluctuation in the inductor. And finally, that is going to be reflected through the upper switch serving as a rectifier. This is the mechanism by which fundamentally boost converter develops voltage gain, as Dan Wolover's thesis really explains. Important point that we want to bring up here is that this mechanism of indirect power conversion incurs both conduction losses and, even worse, incurs the entire AC, switching plus AC magnetics losses. Okay, so the overall strategy to designing high-efficiency power electronic systems is to, number one, minimize indirect power to the minimum feasible, and second, transfer indirect power by most efficient means possible. Boost fails on this part B. Okay, so here is an example of some numbers. So here is a 5 kilowatt 650 volt boost converter example. The left-hand side shows the amount of direct power, that's white, and the amount of indirect power depending on the boost step-up ratio. The higher the step-up ratio is, the more and more of the indirect power is processed. On the right-hand side, you have detailed loss model analysis, what happens at different step-up ratios. And you see as the amount of indirect power goes up, not surprisingly in a real circuit, the amount of AC losses, the switching losses and AC losses in the magnetics go up as well, right? So there's no magic behind this. This really just confirms these fundamental ideas that we tried to introduce in the first place. Right, let's see how boost stands with respect to these Wolover limits on 3 counts. First of all, just as an example, take a boost conversion ratio of 5, right? For a boost conversion ratio of 5, 80% of power is indirect power. So almost all, not quite all, but 80% of power is indirect power. Boost is good in a sense of not processing more indirect power than absolutely necessary. It is actually a circuit that does achieve the lower bound on the indirect power processing. When you look at the switch stresses, however, the lower bound on these switches would be something like 3, in the boost, we're going to have more than 5, and so you're stressing the switches unnecessarily beyond the lower bound that we have for the circuit. And then finally, for the apparent power on the reactive components, we are again quite a bit away from the fundamental lower bound. And so the question is really, can we actually do better? Are there circuit topologies that can get closer to Wolver fundamental limits and process the indirect power, not just at the minimum level, which boost does, but more efficiently, which boost doesn't? Now, if the answer to this question were no, I really wouldn't have this seminar, right? So there's going to be a yes answer coming to that particular question. And of course, the answer is going to be yes. But there's going to be a but to that answer. So yes, it is actually possible to approach the fundamental limits or even meet them. But you cannot do that with the topology that has just 2 switches, right? So you need to construct more complicated topologies and employ more semiconductor devices as switches to in fact approach better the fundamental limits that are established by just theoretical principles. Okay, so we're actually going to take that route and discuss quite a bit along those lines. So let's try to see how we can in fact construct potentially a more efficient boost function. And then I'll show you an application example for that. So what is the idea? So you look at this, again, average switch boost converter model, and you realize, yeah, it looks like I have to have this transformer function inside to bump this voltage up. And I now understand that that transformer function is really where the AC conversion happens. And the more of that I have, the less efficient I'm going to be. So if I look at this diagram right here, I can visualize different circuit ways of realizing the same fundamental structure. The idea would be to take this transformer function and delegate it to a circuit that is capable of more efficiently processing indirect power. Again, taking a simple example here, but those statements are very general. This is really what we've been trying to do, maybe unconsciously, for many years in power electronics. This is perhaps the most fundamental view of how to do things. What is the best way to process indirect power most efficiently? And we realize here we need an indirect power processor here. That's unavoidable. We already reached the Wolver limit, but we can do it better than with these 2 switches. Okay. So the fundamental idea is to say, well, let's just replace that transformer function with a more efficient indirect power processor, and that's going to be how we are going to synthesize a circuit of a more efficient, fundamentally more efficient boost. Right, here is a realization of that idea. So here is the boost circuit constructed of 2 paths. One we are going to call DCX, or a DC transformer. That has exactly that same function that we recognize in the original average model of the boost circuit. And we are going to add in a small auxiliary boost in the bottom path so that we still retain the capability of adjusting the output voltage and regulating the output voltage in the presence of disturbances. So this type of approach that is actually combining dissimilar power converter blocks is where we came up with a name for that approach in general that we call Composite. So power electronics has million modular converters. And we didn't want to use that word to really blur the distinction here. And so we came up with the term composite to distinguish this from the case where the modules that are employed in a circuit are generally of the same type. So we have dissimilar modules, and we compose them into a structure that is conceived in the first place to process the indirect power in the most efficient way possible. So this component right here, this DCX transformer, that's going to be a high efficiency fixed conversion ratio converter. That obviously is going to require more than 2 switches. This already has 2 switches, and so this attempt to make a more efficient boost is going to end up with more switches, as I promised at the beginning.
What are the constraints that you have on those 2 boxes?
Right. So constraints in terms of what? Any constraints.
Kind of variables, either in terms out and V in. I want to understand what are the physical constraints,
Right.
because you're setting up, as far as I'm concerned, an optimization problem.
You can think of that as an optimization problem, right? So the starting point is the spec for this system, right? I want to have this voltage boosted up to that voltage, right? I need to be able to do that. I need to be able to actually get the output voltage. That's no, no, it's not fixed. In fact, by requirement, it has to be adjustable. Let's defer to your question to an application example, and you can see how things work out. Okay, so just give me a second to get to the application, and we'll see how that works. All right, so to introduce the application where this stuff is actually applied for real, it's a drivetrain of an XEV, could be hybrid or plug-in hybrid or EV. And that drivetrain, there are different versions of the architectures, but one particular version that's popular, is, that's been used by Toyota for many years, is the one that has the battery pack on the left-hand side. That's going to be our input voltage, or the battery voltage. It has a boost function inside that is stepping up that voltage to a bus voltage. That bus voltage is the input then to a three-phase drive system consisting of an inverter and the permanent magnet synchronous machine. This is the architecture of a drivetrain you have in a Prius. Okay. So typical values there these days would be in the order of 200 to 300 volts for the battery pack, and the bus voltage that can be anywhere between the battery pack voltage and 800 volts. So here you see some of these numbers coming in that are really application driven. So at the output of the boost function, we have to be able to adjust the output anywhere between the battery input, so we need the conversion ratio 1, all the way up to 800, which means we need the worst case conversion ratio of 4. So we need to be able to electronically achieve 1 to 1 to 1 to 4 conversion requirement. Okay, that's one of the constraints, right? And then we say, how do we actually do that? And then that's what we're going to discuss. The purpose of the DC-DC converter in this case here is fundamentally to decouple the battery pack optimization from the drive system optimization. So you can consider those to be separate systems that can have their own voltage specs and own engineering constraints. Furthermore, so that's design time. Runtime, you have now the ability to dynamically adjust the bus voltage to the inverter, which brings up opportunities to achieve system-level efficiency improvements over drive cycles. You gain the better miles per gallon equivalent, for example. Okay, so in the context of this application, there is one important diagram further that also goes into your question about what are the constraints, what are we trying to do here. Again, application-driven here, what is shown is what are we required to do in terms of the amount of power processed on the vertical axis and the bus voltage on the horizontal axis. So the bus voltage is dynamically going to go up and down depending on the speed of the machine, and the power level is going to go up and down together with the bus voltage depending on how much torque the machine is producing at any given operating point. Which operating points are we looking at? Well, that's really described or prescribed for us by certain standard drive cycles that the vehicle of a certain size is exposed to measure its performance in terms of fuel efficiency, for example. So this particular drive cycle is called the USO6 drive cycle. That consists of a stop-and-go type motion followed by relatively high-speed cruising on a highway and then going back to a more urban environment. It's considered an aggressive drive cycle. Even for that aggressive drive cycle, we spend most of the time at relatively low power levels. And we spend a lot of time, this is the darker the color is, the more often we are at those points. We spend more time at higher bus voltages. So we have a combination of things that are really not quite well satisfied by the boost. We have demand for relatively high step up at relatively low power level compared to the rating of the converter. That's where the conventional boost is highly inefficient for fundamental reasons that are explained earlier. Regardless of how clever circuit designer you are, you're fundamentally limited by the circuit topology itself. Right, so our approach, of course, is to replace the conventional boost with a boost composite. And so this is the boost composite diagram. This was a large project by basically our entire team at CU, including some magician students who did phenomenal work that I still don't know how they did it. So basically all credit goes to really these guys here, who did really great work on some of the results that I'm going to show you a little bit later. So the ideas behind these projects are to say, well, you're going to do this boost function better, fundamentally better, and we're also in the process going to make the whole thing smaller, and you will see how the use of wide bandgap devices plays a role in that process. Right, so here is the boost composite architecture. This is the architecture that fundamentally addresses dominant loss mechanisms. I'll explain what we mean by pass-through mode in just a second. We use the ultra-high efficiency DC transformer module to convert most of the indirect power. We use auxiliary buck and boost modules to provide the regulation capabilities, but those components are never asked to operate with high conversion ratio. They're operated close to 1-to-1 conversion ratio where they're really efficient. The voltage sharing in the architecture allows us to use reduced voltage power devices, which is really a circuit design advantage. We can replace the really slow IGBTs with either silicon or silicon carbide MOSFETs in the process. Right, the way to realize the DCX function, this what I'm claiming is very efficient way of processing indirect power. There are thousands of papers you can consult about that. So the power electronics area has a lot of good examples of how this could be done. And so we're not claiming here this is the only way. In fact, you can do circuit improvements by replacing the topology of the DCX. One that is fairly popular, it's been around for 2 decades right now, people know a lot about it, and it's a good circuit to start with. It's called the dual active bridge. That circuit has advantages of soft switching power devices on both the primary side bridge, the secondary side bridge, is exposing devices to the minimum stresses, and in fact, in terms of indirect power processing, is approaching those fundamental limits that we talked about at the beginning. So this is a way we have actually decided to do the DCX in our system, but I would leave it open for other topologies. You can do LLC type, or you can do various versions of clever resonance circuits. All kinds of ways of doing a fixed conversion ratio are certainly possible. All right, so here's the pass-through mode explained by some numbers. Let's suppose we want to have 200 volt input. We want to have 600 volt output at 50 amps, that's 30 kilowatts. And at that particular operating point, as you're right, there is a system optimization here, and one of the optimization parameters is the conversion ratio of the DCX. You can move that up and down and shift the operating points of the entire system, and you can choose the one that results overall in the best efficiency over drive cycle, for example, which is really what we did. But at the particular operating point, with a conversion ratio of 2, at this point, 200 volt input, 600 volt output, we are really processing power only through the DCX, whereas the buck stage and the boost stage are in pass-through mode. They're not switching at all. They're only direct power passing through and have minimum losses. So you can design this to be better than 98% efficient. These have really low conduction losses at the pass-through modes. And you add up system efficiency. Notice that you're splitting power among different modules in the composite architecture is in fact a little bit better than the efficiency of the DCX itself, because you are really combining the output power through these two power paths, one of which is really, really super efficient because it's doing absolutely nothing. Okay, that's the idea behind the pass-through mode. The important point is that when we go outside of the pass-through mode, our efficiency remains high because, yet again, we are not torturing these components that are involved in regulation. We're exposing them to small levels of indirect power processing and achieving regulation with the minimum additional loss exposed on these modules. Right, here is the more interesting parts to it. You can imagine this lecture could be much longer. You have these three composites out of 3 different pieces. And when you look at the bus voltage requirements and the battery voltage specified by the system, you see that we actually shuffle these modules inside accordingly. So there is a boost-only operation where the DCX is like a short circuit. There is DCX plus buck operation where the boost is in pass-through and the regulation path goes through the buck, and so on. There's DCX plus boost. There is when all three of them in this corner up here. This is our least efficient corner, but it's still much, much more efficient than a traditional boost at that particular point. Control for this system is really fun, and it took a significant effort to develop. But it is entirely possible to actually have closed loop voltage regulation, current limits everywhere that you would require in practice, and do smooth transition between the operating modes, which is a challenging task. Efficiency map shown right here on the left-hand side based on the model, and on the right-hand side measured on a 30 kilowatt system. And you see these numbers are 98%, 97.8, and so on. We do have an actual prototype that is, in fact, operating according to the expectations. In the follow-up stage of this project, we actually went a step further with the goal of minimizing the size of the unit. And when you talk about the size of the unit, the common conception in power electronics is that you increase the frequency and then you reduce the size of inductors and capacitors. Wrong. Okay, this is not like that. So increasing the frequency in some cases can contribute to a smaller size of magnetic components. In most cases, increasing the frequency is not going to affect the size of the capacitive components at all, because the size of those components is related to the RMS currents flowing through the capacitors, not to their internal energy storage. And so increasing the frequency for us here was an attempt to shrink the size of the magnetics. Whether we can do that or not depends on the magnetic materials available and technology of the magnetic components. In this area here, so we are talking about, let's say, a Prius boost converter. What do you think is the switching frequency? It's 30 kilowatts converter in a Prius hybrid. Order of magnitude switching frequency. 10 kilohertz is exactly right. It's exactly 10 kilohertz. The 10 kilohertz component, the inductor, is gigantic. Okay, the capacitor has humongous RMS current, is also a gigantic component. So there is a lot of opportunities to actually shrink that down, and increasing frequency from 10 kilohertz to, let's say, 100 kilohertz is extremely effective because we have phenomenally capable ferrite components in that frequency range. Increasing frequency from 1 megahertz to 10 megahertz is not nearly as effective because we're losing out of steam because of the properties of the magnetic materials. All right, so those are little side comments right here. But in our case, in the automotive application, relatively high power to start with, really low frequency. We have a lot of opportunities to increase frequency up, reduce the size of magnetics. That's what we did using silicon carbide components. As a collaboration with Wolfspeed, they provided these modules with 4 devices. We've used a number of those modules to construct the composite prototype, and this is how it looks like. So here's the composite power stage that is continuous 30 kilowatt, 39 kilowatt peak, using 900 volt, 10 milliohm silicon carbide MOSFETs. It meets all these requirements in terms of voltages we talked about earlier. It has power densities that are higher than what DOE goals are for 20-something. 22 kilowatts per liter, 20 kilowatts per kilogram, and it's employing 240 kilohertz with ferrite planar magnetics. You see here the transformer of the DCX. Then the boost and buck are actually 2-phase configurations. So we have these small inductive components also done in a planar form. And everything is packaged together like a sandwich. Going from top, you have magnetics on top. These are planar magnetics. Then the planar magnetics is sitting on top of a cold plate that has liquid cooling. On the bottom, we have the silicon carbide MOSFET modules that are facing the cold plate from the bottom. And then they're sitting on a power PCB, and the very bottom is the driver and control logic. So it's a sandwich of really these 4 pieces to put it together into relatively nicely packaged form. And some results here. Here's a comparison of the efficiency of a conventional boost and the composite. So the efficiency goes from, let's say, something like 96% to about 98%. that's cutting the losses by a factor of 2. The thermal management goes down by a factor of 2, right? And not just that, we have substantially lower, better efficiency at relatively low power levels where we spend most of the time. So when you look at our results in terms of the CAFE efficiency or a Q factor, P out over P loss, we are about a factor of 3 times better compared to the conventional state-of-the-art technology. This CAFE stands for Corporate Average Fuel Economy, so that prescribes certain drive cycles to go through. So this is a weighted efficiency, not the best efficiency, not the minimum efficiency. This is the efficiency weighted over drive cycle. Now look at this. The number of devices goes from 2 in the boost. How can it be better than 2 devices in the boost? We employ 16 devices in the composite architecture, right? We'll talk a little more about that. Semiconductor area is the same everywhere. Power density is about 5 times higher. Switching frequency is significantly higher. Capacitor size is 5 times lower, and magnetics volume is 5 times lower as well. All right, a little bit of flavor of a different application area. I'm going to jump then forward to a discussion. Totally different application area of power electronics, supplying power to heterogeneous systems that include RF, analog, digital components. So you have a board like this that has all kinds of stuff, RF, ICs, mimics, a digital core, I/O, radio input, radio output, and so on. Right. So when you look at this diagram of a really modern board of this type, you see there is all kinds of other stuff around. What is that for? So here we have everything labeled other than this bunch of these components down here. Power electronics. Okay. So we are really looked at as being a hurdle to these systems. Because you typically have a single DC input. It could be, let's say, 48 volts for a server board or 12 volts for a server board, whatever. And you have the need for multiple tightly regulated DC domains, 1 volt or sub 1 volt for the core, 3.3 volt for I/O, 5 volt, 12 volts for RF, PA, and so on. So the state-of-the-art power conversion is done by putting these blocks in a sort of brute force manner. You end up with taking substantial portion of the system footprint, volume, and weight, and you have to involve multiple conversion stages, some of which are with large step-down ratios, and that is overall inefficient. So here's an example of how you would do it. We actually, a student of mine actually went through a complete database of products from TI. The best, the latest possible products you can buy. And this is what people are doing. You just go to TI site and say, I want this voltage conversion to that voltage conversion, and you pick a component that you like. You can systematically do that and find the best possible solution. So I wouldn't say under the sun, but from a given fairly extensive database. So this is an optimized solution based on state-of-the-art commercially available components. And you basically do this example of 15 volts, 3 volts, 1.2, distribution using 3 power converters arranged in this manner. Okay, how much power is processed by each one and how much losses you have in each one is shown on this diagram. You end up with a total loss of about 6.6 watts, which means efficiency overall is about 90%, and you take a footprint area of 1200 square millimeter. Right, so now when you look at this problem here, a single input and multiple outputs, you have even more opportunities for innovation from a topology point of view. Think composite. Think of minimizing the indirect power processing required to achieve a certain voltage regulation. And this is not a done deal. We are in the process of actually researching this more systematically, but there is a lot of promise to it. So here is a different arrangement. There is making use of DCX blocks arranged in composite manner. You can see this is a buck version that has a DCX combined with a buck converter right here. There is another DCX that is sitting on top of it. So these guys are now sharing the voltage. And that sharing the voltage is achieved by another DCX stage that is shown right here. So this is one version of how, just showing how things can be done better, not necessarily the best possible yet. But here we've cut losses by almost a factor of 3, 2 to 3. We've boosted efficiency by 5%, 2 times lower loss. We've cut the footprint as well. So there's a lot of potential to go beyond what we think is kind of a trademark of power electronics, these standard simple topologies. Okay, so hopefully I've convinced you that there is some value to doing this stuff. and then I can tell you what people are asking me. What are the questions we get from either industry or from academia? You come up to a conference and you show, you've replaced a boost converter with 2 devices with something that is better, but it has 16 devices. Is that actually worth it? Okay, so I have, we're looking into these questions right here. This is a larger number of power devices. In power electronics, counting devices has been endemic for many years. The first thing they look at is how many devices you have. We worked with automotive manufacturer on this. They liked efficiency. They liked everything. I said, oh, well, you need so many devices. It's sort of like a down, looking down at this as being something that's disadvantaged, right? So there's a larger number of devices. And the second item that is brought up, oh, this is complicated to control. Boost is simple. You just have a single duty cycle and you move that up and down. Here you have a variety of control signals that you have to shuffle around and figure out how to do that in ways that people don't generally know. There is a more sophisticated argument beyond just counting the devices that says, well, this is a more complex power stage. You need a larger number of gate drivers. That's true, and that is in fact a problematic issue. More control signals, and you have potentially more difficult interconnect parasitics. It is going to be more difficult to put the bus bars on this. If you look at the high power levels, it's going to be more difficult to interconnect the stuff. And then finally, with many more devices in the power stage, you have the reliability issue come up as a question as well.
What about the scalability?
Right, the scalability is another. I should have actually brought that up. In fact, scalability is really what we are focused on heavily right now. How do we take this concept and extend it to however high voltages or power levels you want? What happens, you can do it, right? The circuit-wise is pretty trivial, but these come back to us in terms of especially reliability is a key point to look into. And also this one here, the more complex stage with more gate drivers and so on, that's also partially related to reliability as well.
Any maintenance issue there?
Well, there is, we can talk a lot about what makes power converters fail, but in terms of the converters that we prefer to build, we have components that do not have expiration date necessarily. Now, they do have some mean time to failure, and you can do all kinds of reliability analysis of these systems. But for example, we like to avoid use of electrolytic caps if possible, because they do have expiration date built in that's known. It's going to fail in some number of years. So maintenance-wise, we would like to build systems that last for very long periods of time. Depending on the application, in the vehicle case, you want to make this system last for the life of the vehicle, which is typically assumed to be like 15 years. In the PV photovoltaic case, you would like the converters to last for 25 years, right? Because that's assumed to be the lifetime of the system. So those demands of how long this should last are coming from the application space.
And so the reliability I understand very well. What about the complexity of the control?
Right.
Does that impact long-term operations?
Well, not necessarily. So I brought this up as discussion points, and I'm going to give you my kind of cut answers to those. And you can see how convincing those answers are. Yeah, I think some need more work, right? So on the large number of... Yeah, there are trade-offs here. The large number of power devices, I think, is a flawed argument. So counting devices is what we should really teach people not to do in power electronics. We've been doing that for a long time. We should get away from that. What we are basically saying here is very simple. You have the same area of the semiconductor material. And in fact, when you put them in 2 devices, they are often cut into little pieces and put together in parallel. Instead of doing that, cut that available area of the semiconductor and arrange those pieces in a better way, a fundamentally better way. So I think the larger number of power devices is a flawed argument. So I think that's, it's difficult to convey to industry and looking forward into almost everyone. But I think I'm ready to make that argument as often as necessary.
When you say reconnect them in different ways, you talk about the topology of the circuit.
Yes. I'm going from 2 devices in a boost to 16 devices in a composite converter. It's the same semiconductor area, pieces rearranged differently. Okay, so from a fundamental cost of power semiconductor point of view, we are even.
Just curious, so do you think that the component count number is proxy that industry uses for reliability.
Yes.
That's where this comes from.
That's where the origins of this counting number of devices from a reliability perspective, right?
This is a single string system, so if anything fails, the whole thing goes.
Correct. Right. There's no redundancy in this system. There's no redundancy in the composite converter. If one device fails, it fails, right?
Right, but that doesn't mean that the whole system is down, which is where, you know, the component count is the flood argument actually.
Correct. Right. And there are opportunities there to address reliability in a more structural manner. You can put some redundancies in and so on. Those are going to require even more devices, perhaps. But that's where we are right now. So in the more complex control, I think that's also a flawed argument. We've been doing digital control for many years. It's absurdly easy to make really sophisticated controls with power electronics. People who don't know how to do that, I think they should go back to school. And I'm not going to take the argument that the control complexity itself or control simplicity is some kind of feature. When I review a paper and say, this control is super simple, unless there is a good context to it, I kind of cringe and say, well, so what? I mean, I don't care really about the complexity of control. So more complex control by itself is really not an issue. We really can learn how to do control of complex power converter topologies really well. These two are a little more difficult to deal with. These are more sophisticated objections to the more devices type. And I think there are opportunities there to look to future work. Higher levels of integration is one opportunity. I'm going to go through 5 minutes of that in just a second. There is packaging side to power electronics as well. That's not necessarily where my group has been on the forefront of research, but is certainly an opportunity as well. Integration definitely does help. If we can actually take advantage of some of the processes available and integrate components, we can in fact reduce the component count and use that to potentially address some of the reliability issues. On the reliability part, I would say that our strongest argument is that we are reducing stresses on the components, relatively speaking, and reduces temperature rise. We've done detailed analysis of reliability for the composite versus conventional boost. Using industry-accepted techniques of calculating mean time to failure, we actually come ahead, not by a small amount, by a substantial amount, because we are using more devices. So by the count, we should be losing, but those devices are exposed to lower stresses. They use gate drivers that are rated at lower currents. That helps a lot. They're operating at lower temperature rise because the converter is much more efficient. So this is open research-wise. All of these points are really open research-wise, except, well, these two in particular. And they require further work, really, to push this type of notion of having more complex power electronics accepted more widely.
So will the deeper integration, is that going to reduce costs?
It certainly will affect cost. You will notice that I didn't put any cost item here. All of those are related to cost one way or another. Cost is a difficult topic to address, especially in an academic seminar. But yes, high level of integration I think is going to be beneficial for multiple reasons. Addressing in particular these 2 points and also the overall cost. So on the integration part, I have just a few minutes left to give you a little bit of a glimpse of what we've done on that end. So we worked on a project that involved use of gallium nitride process, which interestingly has been used for more than 10 years now in the radio frequency power amplifiers routinely. That process was available to us to actually attempt to do circuit integration of power electronics. Now, which level of circuit integration we are talking about here? We are looking at just the fundamental block. And that would be what is called this half-bridge stage, or just a buck stage. 2 power devices, 2 gate drives, all of that integrated on the same chip. Classical design would have this device as discrete, this device as discrete, and then you would have gate driver either integrated or discrete. That's a separate circuit. Our goal here was to integrate everything together because the performance objectives in this case here made it impossible to achieve using conventional technology. Notice the specs here. We want to have pulse width modulation signals in the 10 to 200 megahertz range. We want to be able to change the output voltage, regulate the output voltage with 20 megahertz bandwidth. The purpose of this is to really achieve power control for a radio frequency power amplifier and do that from a voltage that's 20 to 50 volts. So that discounts CMOS, right? You could do something like this in CMOS fairly routinely at the low voltage levels. When you go to 20 to 50 volts, this type of performance power-wise cannot be achieved with CMOS. It cannot be achieved with discrete power devices. So the approach to that was to take advantage of the gallium nitride lateral process to perform that integration step. Here's the process exemplified through this figure of merit, which is the product of on resistance and QG. So here's a comparison to just a discrete silicon MOSFET rated at 50 volts, gallium nitride on silicon like EPC devices, also rated at about 50 volts, and these process devices we had available from a company called Qorvo, and they're in the RF really business. So this is the gallium nitride on silicon carbide type process. It presents interesting circuit design challenges because you have lateral process which makes it possible to put all kinds of devices you like. You can put resistors, capacitors, any number of active devices you like, but you only have NMOS devices available, and plus they're normally on devices. These two are limiting factors for the circuit design challenges. So that's really where we are. The key challenge in this case was the integration of the gate drivers in this process. Yes?
So what is Q? You said that figure of merit is...
Yeah, figure of merit is the product of the on resistance of the switch and the gate charge. Yeah. So we have better figure of merit devices, but we actually want to go much more than that. We want to integrate everything. And so the key challenge is the integration of this high side gate driver. And I have a few pages on that, which I'm proposing I just shuffle through very, very quickly just to give you a glimpse of what can be done. So it's a circuit design. If you're in the IC design business, this is something we can talk more. If you're interested, please let me know. The way we've done the level shifting and the high side gate driver is shown right here. That's called a modified active pull driver that is particularly well suited for an NMOS normally on process. These are the power devices. These are the shotkeys integrated. This is the low side driver that has the same structure but is supplied from a ground and a negative terminal here, whereas this one is supplied from the switching node itself. That's really an innovation here. And the control signals are coming in at these points right here. That's how the layout of this chip looks like. This is about 2 by 2 millimeter chip. Power level up to about 10 watts or so. We employ zero voltage switching in the circuit. That's nothing new, except now we're talking about multiple tens of megahertz switching. So we have dynamically adjusted dead times with about 125 picosecond resolution. There are technical details to make this possible that are important. And here's the experimental results. You know, we did achieve 10 to 200 megahertz PWM switching. This is how the chips are. These are custom designed chips by our students and fabricated in Qorvo process. That's the type of model that I think is very suitable for a university IC-based work. Nothing really super special about filter components, except we use air core inductors. The frequencies are high enough, so we can make use of air core. And the results that we obtain here are illustrated, for example, for some waveforms. So you get 100 megahertz switching with relatively clean switching node waveforms. Just looking at the switching node waveform at 100 megahertz with this level of absence of significant ringing is a sign of a successful attempt. Efficiency is not bad, about 90% for 100 megahertz switching frequency. That's actually not bad at all. We also did even higher levels of integration of having a two-phase, two half bridges integrated together. And we've demonstrated this efficiency results as a function of frequency. 10 megahertz, 97, 98%, 100 megahertz, above 90% type efficiencies. Right, that's compared to what we thought was approximately the prior state of the art. And then this is capable of actually tracking a 20 megahertz waveform successfully with about 85% total efficiency. All right, then there is an extension to a normally off process. That's a different circuit design challenge, and actually a little better efficiency results in that round. And then a little bit of where things are going in this direction. This is a very open area. So integrating power ICs in a gallium nitride lateral process is very new. There are some startups like Navitas Semiconductors have done some attempts in that area, but it's a wide open area for further work, and I think it's very promising in the context of actually designing these highly complex power stages where we can shrink the complexity by higher levels of integration. Takes what we've learned from CMOS and move it to higher power levels and higher voltage levels. This is a piece of collaboration with the Fraunhofer Institute in Freiburg. They put together a half-bridge circuit with Schottky diodes on the same chip. We are working now on actually adding gate drivers to that. That would be a 600-volt capability device. And I think I'm only 3 minutes over time, so not too bad. So opportunities in power electronics go from really understanding the fundamentals, and based on those fundamentals, look into converter topologies and architectures that can, in fact, approach the fundamental limits and process minimum indirect power with highest efficiency. Increased complexity is, I think, a feature we want to look into. It opens up the area for a lot more innovation. With two devices, you can only do so much. You can engineer around them one way or another, but a fundamentally limited circuit cannot be indefinitely improved. A circuit that is fundamentally better can be improved by further engineering and innovations in topology, integration, and devices. Higher levels of integration are certainly crucial in that process. And then finally, you've seen examples. The power electronics is driven by application space. Different considerations in renewable energy, electrified transportation, different considerations in providing power to server farms and so on. We do want to be cognizant of the system requirements and in fact embed that power electronics into the system rather than being viewed as unnecessary evil, right, that they have to add to the system. We want to be part of the system and actually show how putting that together can in fact improve the system, not just the power electronics itself. That's what I had for today.
We do have a couple minutes before we have to run out of here to our lunch break. So any last minute questions?
For the circuit integration, you're using the GAN process. So do you have like P-type GAN?
No. So there is recent work at the HRL. They've actually demonstrated the capability of including a P-type device on a GAN lateral process. That P-type device is substantially inferior in terms of the figure of merit, but it does bring in some potentially interesting circuit design opportunities, right? At least the low power logic gates would be easier to design in that process. Not readily available. There is device research going on in the area of actually getting a P-type to GAN process.
So is that why you use normally on device, or because now you don't have any P-type device, then how do you implement the controller inside?
So a lot of practical difficulties with the process we have at hand. In particular, it's a normally on device. So you have to power the control circuitry before you provide the power to the power stage. Otherwise, it's going to be a short circuit. So yes, far from being practical in a sense of, let's put this in a product type sense. But it's just opening the opportunities of where the integration, we want to look into the integration as a path looking into the future.
This control, was that implemented FPGA based or multiple microcontrollers?
So for the composite boost, we had done everything in microcontrollers. In fact, actually it was a hefty microcontroller for the entire system. For these multiple tens of megahertz converters, it's all FPGA based.